Hello, everybody. Welcome to Outcome 2, Part 1 for equilibrium, acids, and bases. In this section here, we're going to look at acids and bases, particularly Bronsted-Lowry acid bases. So we're going to go over some of the previous acid-base theories that you would have learned in previous chemistry courses, which would include the Arrhenius theory, which is that acids dissociate to produce the hydrogen ion, and bases dissociate to produce the hydroxide ion. So an example of an acid dissociating would be something like HCl dissociating into H plus and Cl minus. A hydroxide ion would be like sodium hydroxide NaOH dissociating into Na plus and OH minus. So that's our product of, as a base, is the hydroxide ion, and this is our hydrogen ion. And then there's also the modified Arrhenius theory, in which acids react with a water molecule to produce the hydronium ion. So we have HCl reacts with H2O to produce Cl minus and H3O plus. We know that when we have H3O plus, it's just another way that saying we have that the hydrogen ion. When we check for pH, we're actually checking the hydronium ion concentration, is essentially what that scale is. And then we can also have bases react with a water molecule to produce a hydroxide ion. So we can have something like CO3 2 minus reacts with water to produce HCO3 minus plus OH minus. And then we can have HCO3 minus react with water to produce H2CO3 plus OH minus again. We're going to look at a theory called Bronsted-Lowry, which essentially is a theory on acids and bases. And so the scientists of Bronsted and Lowry, these scientists focused on the role of an acid and a base in a reaction rather than or the products of the reaction. So acidic or basic properties of their aqueous solutions. So Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So HCl reacting with water produces H3O plus. I'm having issues with my pen here. There we go. And Cl minus. And what happens is that this H is actually being donated onto the H2O. And something like NH3 reacts with water to produce OH minus, which is aqueous, and NH4 plus. However, though, the H is coming off the water, like so. So Bronsted-Lowry acid is a proton donor, a Bronsted-Lowry base is a proton acceptor. Water does not have to be one of the reactants. For example, hydronium ions present in a hydrochloric acid solution can react directly with dissolved ammonia molecules. So we can have this acid here of H3O plus reacts with NH3 to produce H2O and NH4. In fact, water does not even have to be present, as evidenced by the reaction of hydrogen chloride and ammonia gas. So we have HCl and H3 produces NH4Cl. So what we notice here is that water does not have to be present as a reactant in Bronsted-Lowry theory. All right, wants us to identify the Bronsted-Lowry acid and bases in the following reaction. So we take a look at this here. We have HCO3 minus reacting with water to produce OH minus. We said that a Bronsted-Lowry acid is a proton donor, which means that water is our acid, and HCO3 minus is our base. In the next example with HCO3 minus reacting again with H2O, it is at equilibrium. However, though, our product is CO3 minus and H3O plus, meaning that water is our base this time, and HCO3 minus is our acid. And the theoretical term, amphiprotic, describes any entity, ion, or molecule having the ability to either accept or donate a proton. The root word of amphiprotic is amphi, so maybe you're thinking amphibious, where a species can breathe inside and outside water. All right. So we have a couple different reactions here, and we have a Kc value, which we'll talk about in a bit. Well, what I will say, though, for now is that this reaction is much more favorable as we have a much higher Kc value. All right, a couple of examples here for you to work through. I'm going to leave these for now as I feel that you should work on them on your own. So we're going to hop on to the next page here, which is talking about conjugate acids and bases. So according to the Bronsted-Lowry concept, acid-base reactions involve the transfer of a proton. So essentially a proton is usually going to be our H+, but it can be something else. So these reactions are universally reversible and always result in an acid-base equilibrium. Both forward and reverse reactions involve Bronsted-Lowry acids and bases. So here we have acetic acid, CH3COOH. It is donating an H to the base, and then the base, which is water, is accepting that H+. And then on the other side, what's happening is that if we go the other way, we see that our acid is H3O plus and our base is CH3COO minus. So a conjugate acid base pair is a pair of substances with formulas that differ only by a proton. So when we rewrite this reaction out, we have CH3COH aqueous reacting with H2O, which is a liquid, at equilibrium to produce CH3COO minus aqueous plus H3O plus, which is aqueous. And we know that this is our acid. We know that H2O is our base. And we said this was the other base, and this is the other acid. So when you're dealing with finding your conjugate acid and bases, your conjugate base is what looks like your acid. So CH3COO minus is the conjugate base of our acid, which is CH3COOH. So conjugate base. And then H2O, our base, we're oftentimes going to write conjugate as CONJ, period. Conjugate, acid, like so. Could have done this the opposite way, which we said, okay, H2O is our base. It has to accept a proton, and then that way it has the conjugate acid. Few examples here for you to work through. I'm going to do A, and then you're going to do B and C. And then you can check your answers in the completed notes. So HCO3 minus, CS2 minus produces HS minus, and CO3 2 minus. So what we see is that H is here is being donated, so that means that this is our acid, this is our base, and then this is our conjugate base. That means that HS is our conjugate acid. All right, hopefully that helps explain some of a little bit more about acids, just a different way of looking at it in the theory of the Bronsted-Lowry theory. In the next video, we're going to go over, after we get through this blank page, and that, we're going to look at predicting Bronsted-Lowry reactions. All right, so kind of continuing on with what we just started. So Bronsted-Lowry, just a different way of looking at it, builds upon Arrhenius, except now we're dealing with a proton a proton transfer, and a proton donor. If you have any questions, let me know, and take care.